So we are starting with 5.3 today, which is the sum and difference identities of cosine. And like I said, we're going to cover both 5.3 and 5.4 today because 5.4 is the sum and difference identities of sine and tangent, so they really all go together. One thing, though, to start off with is just remember that cosine of a minus b, like within the parentheses, does not guarantee cosine a minus cosine b. That's why we're going to have some of these different identities to help us know what these actually equal. So cosine of a sum, so that's where you have cosine of a plus b inside, is going to break into cosine a, cosine b, minus sine a, minus sine b. Then the cosine of a difference, that's where the a and b are being subtracted within the cosine, is where you have cosine a, cosine b, plus sine a, sine b. So notice that on cosine, the signs are opposite. If you are doing a sum, then over here you will have a subtraction. If you're doing a difference, then over here you will have an addition. But it's still cosine a, cosine b first, and then minus or plus the sine a, sine b. And these are the identities we're going to use in order to find exact values and do some verifications in this section. Are we good for me to move the actual notes part? Okay. Because the first type of problem that you encounter is finding the exact value of different trigonometric functions, or different, in this case, cosine functions, because that's what we're doing in this section. If you type cosine of 15 degrees into your calculator, you will get a decimal representation, and that's great. That's not what they want here. They don't want a decimal. If it says exact, then you're going to have fractions, you're going to have radicals, you're going to have all kinds of stuff. But you're not going to have a decimal. So don't be tempted to put a decimal in here. And we're going to use our different identities in order to find these exact values. So if we just saw like our cosine of a sum and cosine of a difference, then we probably should use one of those as an identity in order to come up with this. Now, if I'm thinking about cosine of 15, I could do it as a sum, where I think, okay, well, that'd be like cosine of 7 plus cosine of 8. But off the top of my head, I don't know what cosine of 7 and cosine of 8 is. So how about we think of it as a difference, because hopefully from back in the previous chapters, somewhere in there you have the unit circle that you can either reference or you have memorized, where you can think, okay, wait a second, I know we've seen cosine of 45, and I know we've seen cosine of 30, and 45 minus 30 does give me 15. So I can rewrite this as cosine of 45 degrees minus 30 degrees. And now I have the cosine of a difference. So I can use my cosine of a difference identity in order to expand this and come up with the exact value. So cosine of a difference. We're going to take cosine of A, cosine B, plus sine A, sine B. That means I'm going to have cosine of A, which is 45 degrees, cosine of B, which is 30 degrees. And since it's a minus, I'm switching to plus. Sine of 45 degrees, sine of 30 degrees. Now we have to actually know what these are. Cosine of 45 degrees. Yep, square root of 2 over 2. Cosine of 30 degrees. Square root of 3 over 2. Yeah. Plus, and then the sine of 45 degrees is the same thing as cosine. And then the sine of 30 degrees, 1/2. So I'm plugging in the values that we know it to be. And if you don't know it to be that, I strongly encourage you to memorize your unit circle. Or memorize the tables where we have the cosine and sine and tangents broken down for the 30, 60, 90, 45 degree triangles. Those will be very helpful. So now I'm going to multiply these together. So I get the square root of 6 over 4 plus the square root of 2 over 4. Combine them together, and I get the square root of 6 plus the square root of 2 all over 4. And you're like, well, that looks gross. But it is the exact value that cosine of 15 degrees equals. The big thing here is because you will have fractions, you will have radicals, is you have to make sure that, one, it's simplified as far as possible, and two, that you have rationalized your denominator, which means you can't leave a radical in your denominator. If you have a radical in your denominator, you're not done. But in this case, I can't combine radical 6 with radical 2. Neither of them simplify any further. Don't try and do any magic math here where you're like, okay, well, this has 2, 2, and 2. Don't do that. That's not real math. So this is as far as you can take it, and that is the correct answer. What about cosine of 5 pi over 12? That one's a bit different because it's using our radians instead of degrees, but we need to think of it in terms of like addition or subtraction. So over here to the side, I'm just going to kind of play around with 5 pi over 12. Let's break that apart. And if I try to do a sum with it, well, that would be 3 pi over 12 plus 2 pi over 12, yeah? If we add those together, we get 5 pi over 12. But those simplified are pi over 4 and pi over 6. I bet you on our unit circle we have pi over 4s and pi's over 6s. So that's always what I'm going to try and get to, is something that lays on the unit circle, because then I can reference my unit circle for my exact values for these cosines and sines and tangents as we move through this. So I could rewrite cosine of 5 pi over 12 as cosine of pi over 4 plus pi over 6. And then I have a sum, a cosine of sums. Cosine of sums is where we have basically what we had up here, but we have a minus in between. To where I will have cosine of pi over 4, cosine of pi over 6, minus sine of pi over 4, sine of pi over 6. What is cosine of pi over 4? Square root of 2 over 2. And if you don't know your unit circle, you can use your calculator to find these different values. You just have to make sure that you're in the correct mode. If it gives it to you with degrees, you got to be in your degree mode. If it gives it to you in radians, you got to be in your radian mode. And then you have to know how to use your calculator in such a way that you're not going to get decimals out, because you don't want decimals. That's another reason why the unit circle is actually so much more helpful, because you don't have to worry about any of those conversions or changing settings on your calculator. So cosine of pi over 6, square root of 3 over 2, minus sine of pi over 4, square root of 2 over 2, times 1/2. This looks a lot like the last problem. Square root of 6 over 4 minus square root of 2 over 4, square root of 6 minus square root of 2 all over 4. So very, very, very similar to the last one. Now, obviously, they're not all going to be exactly the same, but this one was similar. So for both of these first two, we started off with a single cosine, and then we expanded it using either the sum or the difference identities, and then we were able to simplify and get the most exact value for it. But they could give you the longer form, and then you have to condense it using that sum or difference identity. So here we have cosine, cosine, minus sine, sine. Since it's a minus, that means I'm going to use my sum, because remember they're opposite. This is my A, this is my B. So this becomes cosine of 87 plus 93. I'm condensing it. I'm going the opposite direction. 87 and 93 is cosine of 180. So if you think about your unit circle, what is the x value at 180 degrees? -1. In my notes, for some reason, I wrote 1, but it's -1. questions on how we are going forwards or backwards with these? Again, no decimals. Okay? So let's learn, because I mean you don't have enough identities, let's learn some more. I'll slide that up. I can leave that up there a little bit. Well, this one's co-function identities. It's another form of identities that you're going to use. Co-function identities say that 90 degrees minus whatever your theta is equals its co-function. So cosine's co-function is sine. Tangent's co-function is cotangent. Sine is cosine. Secant is cosecant. So they're a little different. They're not the inverse identities. We've had those in the past. That's not what these are. Bless you. These are 90 degrees minus theta. So they associate with different trigonometric functions. You ready to try one of these? Do we have them all written down? It's okay if you don't. I'll wait another minute. Silence is a yes. Okay. We're going to find the exact value. Again, there's that terminology. Exact value of our theta or our x that satisfies this given information. We have cotangent of theta equals tangent of 25 degrees. So we just saw that cotangent theta equals what in terms of our cofunction? Yeah, it equals tangent of 90 minus theta, right? So instead of writing cotangent of theta, we could write tangent of 90 minus theta. And I didn't do anything to the right-hand side. All I did was I changed cotangent of theta into tangent of theta. Okay? Now, if we have tangents on both sides, you can kind of ignore it, or if that bothers you because you don't like to ignore it, what we're really doing is taking the inverse tangent to both sides, and that cancels it out. We've done this in the past. That way we can just look at what's inside of our tangent so that we can solve for our theta, because this is just like an algebra problem. We're trying to figure out what theta is. So we have 90 degrees minus theta equals 25 degrees. So to solve this using algebra, we would subtract the 90 and divide by a negative so that we get theta equals 65 degrees. And that's all we have to do. we use these identities in order to get the same trigonometric function on both sides, because then you can just kind of ignore it and you can look at what's inside of your trigonometric function and then solve for your theta. If it gives it to you with theta being degrees somewhere up here, then you're going to get degrees at the end. If you are given theta in terms of radians, then you should get theta in terms of radians at the end. So let's look at sine theta equals cosine of negative 30 degrees. Since we have the 30 degrees over here, the cosine of negative 30, let's get sine in terms of cosine. So sine theta equals what using our cofunctions? We don't know. We can look. So sine theta equals what? Huh? Maybe right here, our very first one. Because see, it's over here. Sine theta equals, we can rewrite it in terms of cosine, which will help us because then we'll have cosine on both sides. So this will be cosine of 90 degrees minus theta equals cosine of negative 30 degrees. Now we do the exact same process just like we did on the last one. We have cosines on both sides, so we can ignore them. So that we have 90 degrees minus theta equals a negative 30 degrees. However you want to move those things around, add the theta, add the 30, whatever you want to do, you should end up with theta equals 120. And this is secant. Secant, not sex. It did say sex, but I had to fix it. That's why I like using theta better. So for the last one, we are given cosecant of 3 pi over 4 equals secant of x. So it's the side over here, the secant of x side, that we're going to end up changing. Okay? So what does secant of x equal based on our cofunctions? Yeah. So this side over here, my left side, I'm not doing anything with. But over here on the right-hand side, you just said that I can change it into cosecant of 90 degrees minus, it says theta, but we're going to change it to x because they gave it to us in x. Now here's the problem though. Now we have a problem that has radians and degrees at the same time. And since they give us radians, we need to stick with radians. So I need to know, I need to be able to convert this over here. So what it was though, what we had right here was we had this equals secant of 90 is what I really need to know. What is secant of 90 degrees in its exact radian form? Well, it's pi over 2. So in here, instead of writing 90, I need to write pi over 2. That way I have radians and radians. So that I would have 3 pi over 4 equals pi over 2 minus x. Because we don't want to have multiple different units going on at the same time. So again, you can think about either moving your x and then subtracting the 3 pi over 4, or subtracting the pi over 2 and then multiplying both sides by a negative. But you end up getting negative pi over 4 equals x. Whatever form they give you, you've got to put that out at the end. Degrees, you get degrees. Radians, you're going to get radians. And you might have to do a conversion somewhere in there, because all of our cofunction identities are given to us in terms of degrees. But if they give you radians, you're going to have to do a conversion and convert that over. Now, so far, the only style of problems we've encountered are finding these exact values for these different trigonometric functions, which are great. But that's not the only type of problem you're going to have. Sometimes you're going to have, I kind of consider them to be condensing problems, where you're going to have something that's more spread out and you have to bring it all together into one single trigonometric function. And that's what the next one's going to do. I try to give you an example of pretty much anything you could encounter in any of these sections. So we're going to write cosine of 180 degrees minus theta. We're going to write all of that as one single trigonometric function of theta alone. So right now what it is it's a difference. It's a cosine of differences. And we don't want that. We want it to just be like a nice single cosine. So in order to actually figure that out, we're going to actually spread it first, because since it's a cosine of differences, we can actually separate this out, where we have cosine of 180 minus theta. I'm just rewriting it. Using our identity, we know that this is cosine of 180 degrees, cosine of theta. Since it was a difference, we have a plus over here, sine of 180, sine of theta. And I know I went off the screen, sorry. It's not quite wide enough. Now, what is cosine of 180? Yeah, -1. And what is sine of 180? 0. Well, that's going to be really nice, because 0 times sine of theta means all of that's going to go away, leaving me with a negative cosine of theta. And that's it. I got theta into a single trigonometric function. There's no adding, subtracting. There's nothing else involved. It went to a nice, cohesive, single function. All I had to do was expand it using my identity and then simplify using the fact of what cosine of 180 and sine of 180 is. Questions on that one? Okay. The last one for this section is a verify problem. We did verifications in 5.1 and 5.2. That's where they give you an entire equation and they want you to prove that it's true. And you do that by looking at one or both of the sides and trying to manipulate it around to look like the other one. And we're going to use all of our different functions and identities that we know of from everything that we've ever encountered. Now, there was multiple different ways to go about this. We can deal with the left side, we can deal with the right side, we can deal with both sides. But here's something that I notice pretty quickly, is that the left side seems a lot more complicated than the right side, right? And we're in the section titled cosine, what is it? Sum and difference identities of cosine. And I know for a fact that secant is 1 over cosine, right? So I'm going to play around with this left side, and I'm going to see if I can't get it to look like negative cosecant of x. Because what I know is that 1 over cosine of 3 pi over 2 minus x is the same thing as secant of 3 pi over 2 minus x. That's just using the definition of secant in terms of cosine. But then what do you know about the bottom? It's a difference. It's a cosine of differences. So we can expand that out where we're going to have a really big fraction. Because cosine of 3 pi over 2 minus x is the same thing as cosine. I want to make sure I'm still on the screen for you guys. Barely. Cosine of 3 pi over 2 cosine of x plus sine of 3 pi over 2 sine of x. And as we saw play out in the last problem, hopefully some of this is going to kind of fall away based on the information of cosine of 3 pi over 2 and sine of 3 pi over 2. 3 pi over 2 is 270. So what is the x value at 270? 0. So we'll have 0 cosine x plus, what is the y value at 270? -1. But that first part's going to completely go away, which is super nice, because 0 times anything is 0, leaving us with 1 over negative sine of x. But what do we know 1 over sine to be? Cosecant. And since we have the negative, that's fine. It just becomes negative cosecant of x, which was what we were trying to get to anyways. So we just verified that those are in fact equal. And we did that using our sum and differences of cosines. Questions, comments? I know it's a lot of identities. The more you play with them, the more you'll see how they fit together. All right, let's get down our sine differences and sums and our tangent differences and sums. Like I said, this was 5.3. 5.4 is the same identities. I mean, they're not the same because they're for sine and tangent. But we're going to be doing the same style of problems. We're just doing them with sine and tangents. Again, this is why I'm not a big meanie in making you memorize all these. Could you imagine if you had to memorize all these things? I feel like we could spend the whole semester in chapter 5 just learning all these different ones by memory. Now, that being said, obviously the more you use them, the better and quicker they're going to come to you. But that's a whole lot of identities, and I'm not that mean. So, sine of a sum or a difference, it splits differently than your cosine one did. You'll have sine of A, cosine of B, plus cosine of A, sine of B. So it does different stuff than your cosine, which hopefully you expect that. But we're going to use these different identities, just like we did just a few minutes ago, to find the exact value of sines and tangents, and to find, like, get theta alone, and to verify. We're going to do the exact same things. Just using different identities. first style of problem that we encountered in the last section was to find the exact value, and that's what we're going to do here. We're going to find the exact value of sine of 75. That's our first one. And again, you could approach this different ways. Like I could do, okay, well that's sine of 100 minus sine of 25, and that's true. But I don't know what sine of 100 is or sine of 25. So I'm always going to try and use 30, 60, 90, or 45 or something like that in order to get these different values, because I know what those are, or I can figure out what those are pretty easily from my unit circle. So if I have sine of 75, I can write that as sine of 45 and sine of 30. And I can figure out my sine of 45 and sine of 30. So now I have a sine of sums. So sine of sums becomes sine of 45 degrees cosine of 30 degrees plus cosine of 45 degrees sine of 30 degrees. That's just coming straight off of our identity. It's the first identity on today's notes, or this section's notes. So now I need to know what sine of 45 degrees is. Well, sine of 45 degrees is the same as cosine of 45 degrees, and we've seen it multiple times this morning as square root of 2 over 2. Cosine of 30 is what? Yeah, square root of 3 over 2 plus square root of 2 over 2 times 1/2. This looks a lot like something else we did. A whole lot. Square root of 6 over 4 plus square root of 2 over 4, maybe because it's the exact same thing that we had earlier. That was the exact same answer that we got for the exact value of cosine of 15. Which should make sense, because 15 and 75 add together to give us what? 90. And that means that we've utilized, in this roundabout way, we've utilized our cofunction identities. Now, I don't expect you to recognize that. I just expect you to be able to do the problem. But it is interesting when they work out like that. Okay, let's look at a tangent. 7 pi over 12. Again, I would start with this one a lot like we did the part B on 5.3, where we split it up, because 7 pi over 12 is the same thing as 3 pi over 12 plus 4 pi over 12, which gives me pi over 4 and pi over 3. Both of those can be found on the unit circle, so I'm probably going to use those, because I like to stay in the unit circle as much as possible. So tangent of pi over 3 plus pi over 4. So we have a sum, a tangent of sums. Tangent's got a lot more going on than the sines and the cosines, because the tangent of sums means we have tangent of A, so tangent of pi over 3 plus tangent of B plus tangent of pi over 4 all over 1 minus tangent of A times tangent of B. So there's a lot more to do with this. But that's okay, because it's all going to really work the same way. The problem is that we're going to have to do some rationalizing of our denominator in this one. What is tangent of pi over 3? Square root of 3. And what is tangent of pi over 4? 1. So we have 1 minus square root of 3 times 1. I'm not going to write the times 1, though, since this goes to 1. Now, in our denominator, we have 1 minus square root of 3. That's a problem. So we need to rationalize our denominator so that we can get the radical out of it. How do we rationalize the denominator, though, when we have a binomial like this in the denominator with a radical? Close, not reciprocal. We will multiply it by 1 plus the square root of 3. That's called the conjugate. So the conjugate is whatever the denominator is in terms of the binomial, and all you do is switch that middle term, like switch the sign. If it's negative, you switch it to positive. If it was positive, you switch it to negative. So we're going to multiply the top and the bottom by 1 plus square root of 3. 1 plus square root of 3. The reason why this works is because now we have a binomial times a binomial, and so we have to FOIL. When we FOIL on the bottom, what will happen is we'll take 1 times square root of 3, which will be positive square roots of 3, and then you get the minus square roots of 3, so that square root of 3 term goes away entirely. And that's why we can multiply by the conjugate. But we do need to FOIL both the top and the bottom in order to get rid of all of this. So on top, I'll take radical 3 times 1, which is radical 3. So that's first. Outer will give me a positive 3. Inner will give me a positive 1. Last will give me a radical 3. All over on the bottom, what I end up with is 1 minus 3. So I have 4 plus 2 square roots of 3 on top, all over a negative 2 on bottom. Don't do magic math there when you add your radical 3 and think you get radical 6. That's not how that works. What you're doing is you say you have 1 radical 3 and you have another radical 3 giving you 2 radical 3s. Notice here we have a 4, a 2, and a negative 2, so this can all be simplified further. So that I have a negative 2 minus radical 3 in the end. What I did is I took 4 divided by negative 2 and the 2 radical 3 divided by negative 2 to simplify that. So there's definitely more algebra involved, especially with the tangent, because the tangent, you have a fraction. And so if you have a radical, you've got to keep going until you get no radicals in the denominator and it's completely simplified. Questions? Okay. This last one is where they gave it to us in the expanded form, and we're going to shrink it and simplify it. Sine 40 cosine 160 minus cosine 40 sine 160. So we need to figure out which of our identities this happens to be. We know it's not tangent. And since we're in the sine section, we know it's either the sine of a sum or the sine of differences. Since it's subtraction and sine works like with the same sign, we know that this is going to be sine of a difference, where this is my A and this is my B. So I can rewrite this, instead of this whole big long spiel, I can rewrite it as sine of 40 degrees minus 160 degrees. So I condensed it using my identity. 40 take away 160 is negative 120. If you remember, having the negative inside of my sign, I can actually pull it out front of my sign like this. So I need to know what the sine of 120 is, which is my y value, which should be positive, but then I have this negative out here, so I'm going to get a negative. Yeah, negative square roots of 3 all over 2. That's a 30-60 triangle, 30-60-90 triangle, or angle in quadrant 2. Write each with theta alone. Well, we have sine of 30 degrees plus theta. So this is a sine of sums. So we're going to expand it using that identity. Sine of sums expanded will give me sine of 30 degrees cosine of theta plus cosine of 30 degrees sine of theta. Well, what is sine of 30? 1/2. And what is cosine of 30? Square roots of 3 over 2. Okay, so that means I have cosine theta plus square roots of 3 sine theta all over 2. All I did was I joined them together. If you don't like that I maybe skipped a step, I did cosine theta over 2 plus square roots of 3 sine theta over 2, and then I joined them together. Because it wants it with theta all by itself, and it also wants it all in one term. And so I need to join it all the way up. Okay, I have two others like this in the notes. I have one for tangent and another one for sine, because the sign down here deals with the difference, sign of differences. I'm going to skip those, at least for the lecture, so we can do our verify problem, so that you get an example of the verify problem before the end of the class. But just know those are in the notes. I do work them out. They work the exact same way that the one we just did was. But I want to make sure we get to the verify problem. We have verify sine of all this yuck plus cosine of different yuck equals cosine theta. Those are very mathematical terms, by the way. So obviously looking at our equation, which side's more complicated? Yeah, that left side. Left side is way more complicated. So that's the side we're going to play with. And what makes it so complicated, or more complicated than the previous ones that we've had, is we have the sine of the sum and we have cosine of a sum. So we're dealing with the identities from today, from 5.4, and the identities from this, like earlier today, of 5.3. So we're going to have to expand both of these in order to see what simplifies. So if I'm looking at the sine of sums, this is going to give me sine of pi over 6 cosine theta plus cosine pi over 6 sine theta. And that is just for that first bit. This part right here, this cosine of sums, splits as well to become cosine of pi over 3 cosine of theta. Sorry, I'm going to try and keep it all on the screen. I might have to zoom out. Minus sine of pi over 3 sine theta. Let me zoom out just a little bit. When they get that long, it's hard to get them all to fit. Okay. Now, obviously, I can't do anything with the theta parts, but sine of pi over 6, that's 1/2. Cosine theta. Cosine of pi over 6, that's 3 pi's over, or radical 3 over 2. And then I still have the sine theta. Cosine pi over 3, that's 1/2. And then over here, I have sine of pi over 3, which is, again, the square roots of 3 over 2. doesn't look like a 1. Let me make that look like a 1. So notice I have a positive square root of 3 over 2 sine theta and a negative square root of 3 over 2 sine theta. So those are going to cancel out. So that's nice. And then what am I left with? A half cosine and a half cosine, which gives me cosine, which was where I was trying to get initially. So sometimes they look super gross, but really all we're doing is applying a single identity, or in this case we did 2 different identities, but then a lot of stuff ends up canceling out or simplifying in the process. So don't let the appearance intimidate you. Okay?